All right, welcome again. This time we will talk about regression analysis. And as always, the main thing to remember is that we are doing things that are very similar in their structure and their form to the previous analysis. So there's a lot of relationship between ANOVA and regression analysis, and the way we do the analysis is also very similar to factor analysis and so on. So the main thing here is to remember that you already know a lot about how to do these things. Okay, so in regression analysis we have a situation which is that we have a dependent variable which is interval scale, so it's a continuous variable, and we have explaining or independent variables that also are on an interval scale, either one or several. So where ANOVA has is similarly an interval scale dependent variable, but categorical scale variables as independent variables explaining the variance. Here you can have continuous variables, interval scale variables. And assumptions are similar to those previously. So for a regression analysis to work nicely, we would need variables that are normally distributed. And typically the covariation between the variables that we are interested in is linear. There are, however, exceptions to this, and we'll get into that later, but the the assumption we start out with is that the connection between two variables or more would be linear in nature, not something that is very, very strange in its form. But we'll get to that. So here we have two types of linear covariances, and the typical situation would be that we are interested in what kind of a formula, what kind of a, well, this could be a straight line. Here also we would again have, a linear covariance. This one would be positive, this one would be negative. And then we would have here a situation where there's something like exponential growth, but not a linear connection between the two variables. All right, so here we have a real situation. So the x scale, or the axis, has the time that the students, the pupils, have spent on the different tests. So the whole time that they have used to get the results here, and then the combination of all the scales. So you are doing better if you have good results in all the scales, and less well if you don't have. And here you can see that there is actually at least a linear connection, and that has, been tested here. So it goes, it has the formula of a line. So there's a coefficient telling how steep the line is. So this would be 0, and that would be 1, and then we have something a little bit less, plus 0.78. But equally, you could have something like minus 0.5 or so. But that would be tell something. Then minus would be like this. That coefficient here tells of which way the line is going, and then there's a here this tells us the kind of a plus b times x. So that would be the term for how where does the if we have 0 here in x, so that would be somewhere here. Where will the line cut the y-axis? That would be very close to 0 in this case, but slightly below it. So at precisely minus 0.05. So now we know what this line formula actually has in it. Well, what would be our interpretation? Well, first of all, those who take a very short time to answer all the different scales in that test that was used, also sorry, in that testing situation, they get the poorest results. Then you have here a connection that is clearly quite strong. There might actually be a slight curvilinear tendency here, so we could try out also a different form for to describe this covariance. It might be that we have a steeper curve here and flatter here. So you can already, when you look at the picture, try to figure out what we could do to improve our fit. But this is a strong coefficient as it is 0.78. So this would, even as a simple linear covariation, this is strong. Okay, that's number one. Number two, how do we interpret this? Well, we spoke about this. The other end here, you can see that there's a tendency to get higher results if you use more time, but it's no guarantee. So there are a few kids who use a great amount of time, but still get pretty average results. Well, this is clearly better than average, but still. And the kid who has gotten the best results uses a relatively average amount of time. So really quick, fast thinker. How do we go about this? Well, as previously, we again we'll do this so that you can see for yourself in SPSS, but again, the idea is you select from the menu, analyze, the regression, and then linear regression, if that is what we are out to try out. And usually we start out by trying out the linear regression and then maybe make it more complicated. And then we can select one dependent variable or one dependent variable and one or more independent variables, and you press OK. So this far, everything looks precisely the same as with factor analysis or especially ANOVA. And you have both dependent and independent variables just as in ANOVA. And the only thing is that now they are all the variables are continuous variables, so not categorical. And then you press OK. And the first thing that comes is a kind of, I don't think it's a very good table, but it tells us, makes us remember what we have been doing. So here it says that we have enjoyment of science, the only explaining variable, the only independent variable that we have here, and as a dependent variable, the PISA science factor. So does enjoyment of science explain variance in the PISA science factor? So knowledge in science. And there we have it. And so we get to the first results of this very simple regression analysis. And with one variable, the R here can be interpreted, well, it's actually the correlation between the independent and the dependent variable. So the correlation is directly here. Then we have R square, which is very close to the effect size in its interpretation. So here, the R square tells us how many % of the dependent variable is explained by the independent variable or variables, which we can call predictors from now on, because that's what the program also does here. Okay, so if we now look at this R square, it tells us that 10.9 or roughly 11% of the PISA science knowledge test results are explained by the variable enjoyment of science. Can we say that there is a direct causal relationship? Not really, no. We would need to first measure enjoyment of science and then later on PISA science knowledge to kind of get at the causal relationship. But here we are speaking with the terms of the model. So that's why we are talking about predictors and interpreting the R square as explained variance. We go ahead, and you get an ANOVA table that is exactly similar to that of the analysis of variance. And it also does precisely the same thing. So we have here the degrees of freedom, just as in analysis of variance here. And we have the test statistic, the F, which is again similar both in how it's written up and also in its interpretation. And finally, the significance value. So all in all, this page is exactly familiar to us already. And here we would typically, before we start testing, we would form a hypothesis, which would be that there is a connection between these variables, the science attitudes and the science knowledge factor. And we would also select a level of significance to test our hypothesis with. So here, for instance, we would take a 5% risk of being wrong, which means that we are 95% sure about that there is a connection if we accept the model with a 5% risk. Here actually we can see that it's less than 1%, it's even less than 1 promille. But we should remember to pre-select the risk level that we find acceptable, and then we report that it is lower than, for instance, the p-value of 0.05 or 5%. So there's the F value. Here are the degrees of freedom. And in the text, when you report it, you will also, just as in ANOVA, you would report both the F value, test value, and the degrees of freedom. And not the total one, but the regression degrees of freedom for the regression, so 1, and then comma, and the residual. So again, here we have the degrees of the effect that we are interested in, and the residual is all the noise that we have from statistical error. And finally, we have the significance there. Good. Now then, here we have very much a similar result, but this is good to have a look at this now, because it will get a little bit more complicated when we have more dependent variables. But the third important table here is the coefficient table, and here we have actually we have the same story twice, to be exact. So first, sorry, again, I'm trying to find cursor here. We have it one way, which are the unstandardized coefficients, and then we have the standardized coefficients. So just to make it very simple, here you have the standardized coefficients, so that those would be the coefficients you get if you count a z-score of enjoyment of science and a z-score of the piece of science knowledge, and then you see how well these two z-scores correlate. That correlation would be 0.33, and if we go back here a couple of steps, we can see that that's exactly what we have here. So the correlation and the R, the whole model correlation, when you have just one independent variable, are exactly the same. So far, so good. Second, you don't have a constant here. You remember that we started out with a model where you had a constant and then a coefficient telling how steep the line is. So here you would, with unstandardized version, you would have a constant. Here the constant is exactly 0, because since you have standardized both the x and y, the scientific enjoyment of science and the knowledge of science, since you have standardized both of these, both of them are transformed so that their mean is exactly 0, and that means that they will cut the place where the line will cut the y-axis, which is the constant, that will also be precisely at 0, actually 0, 0. So the origo. And then we have the unstandardized version. These would not be counted from set scores, and here you then have a typical line formula. So you would have a constant term, and then you would have the x factor. The x, this would tell us that it is not very strong, but positive. Okay. Both of these are tested at the same time, so we would here see that the result is statistically significant. So this gives us actually exactly the same result as the previous page, but when we then add more independent variables, then this will change. We have the beta scores. We have the unstandardized B scores, and we have the significance here. Good. Now then, let's take a step further. Example 2, we have again regression analysis with SPSS, but this time with several independent variables. And this part is exactly the same as previously. Sorry, there's a spelling mistake here, but also selecting one independent variable would be the same. But then we select 2 or more independent variables and press OK. So there's a slight change. The first table will be an indication of this. So it still has one dependent variable, but then we have 3 different independent variables. The first here is index of economic, social, and cultural status of the parents or the home. Second, we would have the test anxiety of the student, and the third would be the one that we already had, so enjoyment of science of the student. So one tells about the environment in which you grow up and your parents, and the second and third tell about the way the individual students feel. That's where we have the dependent variable, and again the independent variables. And then it looks the same, but something has changed. So here we now have a situation, Here we now have a situation where the R-square is clearly much higher, so it's no longer 0.3, it's 0.425. Clearly higher, not great still, but it's clearly higher. And also the second exponent of, so the square of R is 0.18. So we have gone up to 18% explanation, explained variance of the PISA results. So now we are interested in seeing, okay, what is it that brings more explanation to our more understanding of the variance of the PISA test results. And again, we get an ANOVA table. This time you can see the difference here, where the regression model now has 3 explaining variables. So from 1 degree of freedom here to 3 degrees of freedom in the model, and that leaves us with a slightly smaller f value, but it's still extremely statistically significant. So the whole model works still nicely. And then we get to the important part of where we actually get our hands on what has changed here. So we still have enjoyment of science here. Since we have added 2 other variables, the variance left for enjoyment of science is slightly smaller. So you remember it was something like 0.3 previously, now it's 0.28. And what is happening here is that test anxiety kind of has a negative covariance with, so it's not a good thing to have a great amount of anxiety. This is small, but still statistically significant coefficient. And likewise, the effect of the home background is also statistically significant. So you can see here, here the statistical significance of each of these independent variables in the model, and you can see that each of them is statistically significant. The standardized coefficients are useful here because they are standardized, they are easy to compare. So we can see here that clearly the strongest influence or the strongest factor behind the test results is enjoyment of science. We have people who clearly feel at home and like the subject, and they get good results also when we test their knowledge. Well, that makes sense, doesn't it? If they are very anxious, it kind of hinders them from maybe doing their utmost, or it may be the other way around. It may be that they are anxious for a good reason. They might have cause to be anxious. We don't know yet. We should try this. We should do some further analysis to try to figure out which way this actually works. And also the home background has some influence, but now you can see which of these is strongest and which of these are weakest, even though each of them is statistically significant. One of them is much stronger than the last one. Okay. And the unstandardized model here we would use for predicting scores in the future. So we will get back to this, but the idea here is that using this formula that is building up here with the different parts here, then we could make if we have a set of data and we get the unstandardized coefficients, we can then from these and the constant term, we can predict what somebody else would get. If we know their enjoyment of science, we know their personality, the test anxiety, and we know their home background, we could make a prognosis of how well they would do in the test. In this case, you could easily also test them, so you don't need to do that. But there are other situations where you, for instance, want to predict if how well students will do if you select them to our program, and then you could have different variables that would give us an strong coefficients here would be good also for predicting what type of what kind of students we should select. So if you have something strong predicting something that you are interested in, how well students are doing in their future studies, for instance, then that kind of a model would be useful for selecting preferably those students who will do better in their future studies. All right. Now we have had one linear regression analysis with one independent factor, then a second one with several independent factors. But as I said, you will also have the possibility of choosing nonlinear regression analysis. That starts in precisely the same way as previously. So you go to Analyze, select Regression, but instead of nonlinear of linear regression, you choose curve estimation, and you select one dependent, and here you can only select one independent variable, and then you choose the model you want to test and press OK. The model in question here can be of different types, so you can have a linear one, you can have, as here, a quadratic. So quadratic would be something like a second degree equation. It might also look like this if it has a negative coefficient. And just as previously, this gives us the information we need. So we have the dependent variable, the PISA general factor, how good they are in the different subjects. We have the equation type, so it's quadratic. It could be something else. And then we have the independent variable, which is how old were you when you arrived in the country of test is Finland or Sweden or the other Nordic countries. And then we can go ahead. So this is, here we get already a lot of results in the next table. So first of all, it gives us the second degree equation with a constant, just as in the first degree equation on the linear equation. Sorry. So here would be the term for the first degree term, and then we would have here the second degree term. So together we have the whole quadratic equation here. It is significant, and the R squared tells us precisely the same as previously. So it tells us how many percent of the dependent variable is explained by the independent variable, but this time in a curvilinear form. And since we see here that it is negative, we can say that, okay, it's U-shaped but downwards opening. And here we already have the result. this non-linear regression analysis, as I said, you can do it also with a linear regression analysis. The nice thing about it, it does this. It produces nice pictures also, so you can try out different. You can at the same time have a linear model and a quadratic model or something else. As you feel comfortable and interested in something, then you can try them out and see which of them works best. And sorry, here the quadratic model clearly tells us that something is happening. The later the student has arrived in the country, immigrated the country in question, the less well they do in the PISA knowledge tests. And actually you can see something else that is also interesting. So since there is a nonlinear relationship here, you can see that for the first 6 or 7 years, the difference is very small, almost no difference here. But if the kids arrive after school has started, then the later they come, the worse the results are. And here already we are close to a difference that is of the size of 1 standard deviation. So that's a big difference. It would make a difference in even individual students' lives. And also you can say that the effect of the Finnish preschool system is rather small. So being in Finland for the preschool is not what changes your future, but if you arrive very late, then the comprehensive school has already taught people a lot, and that is something that is difficult to catch up. Now then, I already spoke about the possibility of predicting with regression analysis. And here we have an example of that. So if you want to predict, then you don't use the standardized coefficients, you use unstandardized ones. And here we would have as the dependent variable, the child's PISA score, and then here the PISA score, and then the father's education and the mother's level of education. And we could then so this has 2 independent variables, father's education and mother's education, and a constant term. And we can use these coefficients here and then a constant term here, and you would have the whole formula to predict. And then we can put in new values here and see what happens with the predicted value. For instance, what would happen if the father's or mother's education was 1 step higher? And of course, this is not for every individual, this is on the average. But if we're predicting what would happen, then this would work nicely. And here we can see, okay, we put in 1 and 1 here, and this would be the result of the whole equation. Now we add one step to the father's education, 1 level, and keep the mother's educational level the same as previously. And we get a raise of 7.6, so not very many points, but still something we do it the other way round, and we can see that because the mother's coefficient is clearly higher than the father's coefficient, the raise, if we add mother's education, is higher than that of father's education. And if both are raised, then we get an even higher result. So here we have already 19 points. Well, you remember that the PISA scores have a, oh, sorry, yeah, forget that, yeah. Anyway, that's where we would, how we could work with this. And if we now would have a situation where this would be different tests results that would have a good prognostic value for how well students will do in their later studies, then we could see what would happen if we select certain students, but we could also just work the other way around and make a level above which we would select the students to our programs. Father's and mother's education are not such, but you understand what I'm after. So you could use this to select the most promising students for your program, or the most promising job applicants for recruitment. Okay. One more thing to be interested in. We have spoken about ANOVA and about regression analysis, but there's a conjuncture where these both are working together. So in ANOVA, there is a possibility of adding what they call covariates, and those are kind of regression terms. And they give you precisely the same result as if you would separately make a regression analysis and try them out. The idea here is that you can control, if you are interested in differences between groups, and then you need to control some variable, then you can use the covariates to control these effects. So how high the child's parents' education level of education is or are, that explains something about the children's PISA results. There's a clear connection here. Now we would be interested in seeing if there still is this connection between parent education and children's PISA results if we control for other variables of the home. So the wealth of the home and possessions of the home. The idea here being that maybe because well-educated parents have the possibility of accumulating wealth, that will, through televisions and books and stuff, influence the children, and they will be better off that way. So for this, we use analysis of variance, which is the short term for it is ANCOVA. So analysis of covariance. Here's where we start out. We have a familiar situation where we have a model. We have the parents' educational level, and we have the the dependent variable. And as you see here, we have a significant connection between the parents' education and the PISA scores. And the partial eta squared can tell us even more. So it's something like 6% of the variance is explained. Still, 94 not explained, but it's a stronger connection than some of the previous ones we have seen. There's something going on. So more educated parents have kids who get better results in the PISA on the average. Now then, what happens if we control for the wealth of the home? We can see it here, the model. If we put in covariates as possessions and wealth of the home, first puts these in, and you can also see here how large a percentage of the variance they explain. So we have 7% from the home possessions, something like 4% from the wealth. And then you can see also that there's still a significant effect of the parental education, but it's now reduced. Still slightly more than half of the variance is there, but it is clearly smaller than it was previously. So something is explained by the home wealth and possessions, but not all of it. So now the second part of this, I was wondering how I would do this most practically, but I thought that instead of having a lot of pictures that I show you, I will just go to the SPSS and show you myself how the thing is, what you can expect to see when you do the analysis for yourself. So here, as previously, you have the menu analyze, and from there, for once, we have a very clear topic selection, so regression, and then you have a lot of different versions. You can play around with the automatic version, but the linear one is the one that I have been demonstrating here, as well as the curve estimation. But there are other things you can do as well. So here you could have a linear with a model with one or more independent variables. Here you could have a curvilinear model. But you can also have, contrary to what typically the regression analysis demands, you can also have here dependent variables that are either have two categories or more categories. And there are other ways of doing the nonlinear modeling also, but this is, I think, more practical. Let's have a look. So now, if you select the linear regression, you can see it here. You can select the dependent variable that you are interested in, and you can select the independent variable or variables. If you want to pick more, then you pick more. Just as in ANOVA, we have here the weight. So just because we have the Scandinavian countries, I have put the Senate weight here so that the countries will be treated as if they were of equal size, or their samples would be of equal size. And we have different statistics here. So usually these two are the most essential ones. We can also try out how well it works. Don't need to go into that too much. From options, you can select the if you have a different methods, you can change the parameters of those. But this is actually the most important part. So if you again have a lot of variables, of independent variables, you should probably click, or my suggestion would be that you click the exclude cases pairwise or replace with mean, so that the model uses all the information that is available, instead of leaving out each case where at least one answer is left one answer is left empty or unanswered. So exclude cases pairwise saves information and makes your model more robust if you have, especially if you have very little data, or if there's a situation where you lose a lot of data because you would use this very strict version. So to me, it's always a little bit strange that they have pre-selected this list-wise instead of the pairwise. And then, as previously, you have different models here. The enter is the one that I would recommend. Then it takes in all the independent variables in the model at the same time. Here, you wouldn't get a difference with the stepwise or the others. But if you have, and I would not recommend having, but if you have a tremendous amount of independent variables, then maybe you want to have a stepwise model where it would pick the best or strongest regression term, strongest of the independent variables first, and then the next strongest, and so on. But this is kind of machine thinking and guesswork, whereas I would recommend that you think first what actually should go into this model, and then you enter it. You are the person who are thinking, and you should be the one who controls your model. But if you are wondering when you read something that they are using a stepwise model and so on, so you know that that's easy to select here. It's not as easy to explain in a theoretically consistent manner. Okay, so use enter usually here, and then you already get the, sorry, here you didn't get any results, I think, but okay, here we would then get the first result that we got. Maybe more interesting is then to have a look at the curve estimation, because that's something that we haven't, it's something slightly different that we haven't been doing. Here again, you can use, you can select one dependent, actually you can select several dependents, but you can select only what I was going to say, one independent variable. And you can then have test different equations. Typically, I would suggest that you would have a constant in your equation, but it's possible to test one without it. More importantly, you want to plot the models that you are have. So you could have here, as I said, either just one nonlinear model. You could compare a linear and a nonlinear model. And you could even have a growth model or a sigmoid also. That would be kind of S-shaped model. Just to see which of these models is closest to the one that your data supports. And you can of course display the ANOVA table there, but here we have already now the nonlinear model compared with the linear model. And you can see that they are pretty close, telling much the same story. But with this nonlinear model, you get the interesting part here with the first 6 or 7 years not being that tremendously influential, and then more effect later on, which is hidden by the linear model. Here you have the equations for both of these. So you can see that both have a constant term. The linear one has only one coefficient to tell which way the line is. So this is a negative coefficient. And then the second degree model has two coefficients. And that's just about it for today, I think. Thank you very much. I hope you will find the interesting use for these methods and find that you will be able to explain things that you would otherwise find it impossible to talk about, or to get your mind around, or to explain to somebody else in a way that is coherent and understandable and communicatable, if that's a word. Anyway, since we started out with the idea that we should have use statistical methods so that we can be convinced of what are how correct our assumptions are, how correct our understanding of the world is. Now we have done a lot of testing, and we can now see, I think, more clearly how we can convince ourselves either that something that we think is there actually is there, and the world is the way we think it is, or get convinced that our previous understanding was wrong and we need to change it. Likewise, with the different methods, I hope that you will be able not only to convince people who already are like-minded and think like you do and are convinced previously of your results, but also be able to clearly and concisely convince people who really wouldn't like to think the way that your results tell that the world actually is. Simply because then we are changing our understanding based on research and not just on because I said so. That is a foundational, I think, good science-based dialogue and discourse all over the world nowadays. Thank you very much. Have a good future. Bye-bye.